We are in the south of Switzerland, but still, we are in Switzerland, so we have to start. So it's a big pleasure to be here and to introduce Simon Scheidegger. Simon, he's professor at HEC since now a few years. He has a background in physics. There he was used to solve quite tough problems, like studying supernovas and things like that. And then he decided probably to move to economics to solve simpler model. But in the end, it didn't work really well. I mean, if you look at his series of work, it's essentially using machine learning to solve all possible crazy, most difficult models to solve, models with heterogeneities, with several factors, 50 sectors, 100 sectors, things like that, frictions, all possible type of such complexities. I think this is a super important area. It's, at least in this part of the talk, I guess, less about looking at data themselves, but it's more about solving complicated models, which can be brought then later to the data with some plausible implications. So it's a great pleasure to have you here, Simon. I will not waste much more of the time of your talk, so please go ahead.
Thank you so much, Fabio, and thank you everyone, first of all, the organizers of putting up this program and having me on the program. It's a great pleasure to be here. Also for the introduction, it's pretty much putting pressure on myself, but after lunch now, let me see what I can deliver on that. So what is this talk about? So it's, I will talk about Gaussian processes applied for solving models. So it will not be a paper, but essentially I will talk about a sequence of some of my papers, but also other papers. The spirit of this conference is machine learning. And when you look at how the literature evolves at the moment, including some of my works, there's a complete hype of using neural nets to solve dynamic structural models. But there's a fair amount of models where I believe Gaussian processes combined with some tools combined with reinforcement learning and then dimension reduction techniques, they're much more elegant and I think better suitable to solve some of those problems than just brute force deep neural networks. So what is this next 50 minutes that you listen to me about? I will give you first a motivation about the types of models we're generically interested in. So it's not, as Fabio said, it's at this point in time not so much about data, but rather about how to solve the models. I mean, clearly, since, as you will see, we can solve models with a lot of state variables, it will also be then a trivial follow-up to structurally estimate them, but that's for another talk. So I will essentially give a tour on how I believe Gaussian processes could be or should be used inside dynamic programming frameworks, so the way how we solve recursive models typically. And then I want to illustrate them on two concrete examples based on my work. One is a paper called Machine Learning for Dynamic Incentive Problems. And the other one is a comprehensive machine learning framework for dynamic portfolio choice problems with transaction costs. It's also joint work with Fabio, who sits here in the room. So like any nasty question, please, you know to whom to address to. And I will try to then also, wrap up with few key takeaways or messages from this talk. But okay, can you hear? I need to stand here. Okay, so I gave a proper presidential address here. No, so I like to walk. No, so dynamic models. Okay, so a lot of contemporary questions in economics and finance we try to model. We try to model with structural models. So what are the types of models questions we want to study? As I will get to the point today, dynamic incentive problems, monetary policy, climate change, I think, is a very important stream of research where you actually need structural models because, the planet goes in a state of the world where it never was. So, if you want to get meaningful policy recommendations, you need models. And now, these structured models, they have a rich set of ingredients, right? So typically you need to put in stochasticity. You need to have different agents in there. So for instance, if you want to study, who is impacted by climate change, by how much, where on this planet, so you need different agents. Models are oftentimes non-linear. We have financial frictions, so we have zero lower bound in our model. We may have borrowing constraints, you name it, but this introduces kinks in the functions you want to approximate. As a consequence, whatever model we write down, we have a lot of parameters. Some of them we may have a good handle on, some of them we may not, and we may have to estimate with structural estimation ex post. So there's many things that go into the magic pot, essentially. And now, how to go about that? And so you all learned in kindergarten, if you essentially want to solve a dynamic model, what you do is you write down a Bellman equation, and the Bellman equation is can I? Oh no, I do it this way. So you have essentially the value function is the maximum of some return function. Think of it as the utility plus the discounted expected utility of tomorrow. I don't want to go through all the details, but the key thing is to which you also remember from kindergarten, is you solve that recursively, meaning you need to approximate the value function, and to do so, you need at the same point on the right-hand side to interpolate on a function. You need to compute an expectation here, so you need to compute an integral. You need to compute a constraint maximization problem for a given state. So this is a non-trivial problem to do only point-wise, but since the models we're interested in, they're non-linear, they're stochastic, so you need to compute a global solution to that. So it's not sufficient to only have a solution at one point, but you need to be able to approximate it on many points on the state space, or if you have an infinite horizon model on the ergodic distribution. So you do that recursively. You need to have the ability to approximate, interpolate, and integrate high-dimensional functions in high-dimensional spaces. And this is, despite it sounds trivial, this is tricky from a formal perspective. Why is it tricky from a formal perspective? So point one, we heard it this morning already, is the curse of dimensionality. So like here, the model you typically have at hand is, it has a state. The state is a vector, can be capital in context of climate change. It can contain mass of carbon in the atmosphere, upper ocean, lower ocean. You name it. You can be very creative about the state, but this is a high-dimensional object. As I said, you want to approximate the function on a domain. So if you have one state and you discretize that, because remember, the models we're interested in, you typically cannot solve analytically, but you want to, or you have to solve them on a computer. So you need to discretize stuff. So if you discretize a state, say, with 5 points, which is nothing, and then you add another state, and then another, so this grows exponentially. So typically after 3 dimensions, if you would do a grid-based approach, you're dead, you're done. Even if you go to a computer with a lot of memory, if you have a reasonable resolution, you cannot go beyond. So you need to have a function approximator that can deal with the curse of dimensionality. That's point one. Then the next thing is, we have nonlinearities in state-of-the-art models. That brings an extra complication. And what do I mean by the extra complication? You need to be able, so here is it's a simulation of a model, whatever it was. So you need to be able to approximate functions that can be constant, and then they have a kink, and then they have complete different change of behavior. So you need to be able to resolve nonlinear functions in high-dimensional spaces. That's another complication. And then one of the very nasty issues when you work in high-dimensional spaces, which people often ignore, is the fact of, I would call it irregular geometries. So what do I mean by that? If you simulate a model, say, with some normal shocks, so here is a two-dimensional projection, that's where the ergodic distribution of your model would be. So in plain English, where does your model live? So here where I have like these points where this amoeba lives. So you notice, if I would solve my model on this entire, cube, how you learn it, not in kindergarten, but in high school, you put your model on your cube, then you solve it everywhere, you have a function, you fit a function over there, then you simulate it. This is what you get. So you don't care about all the spaces which are white. Now in 2 dimensions, that means essentially, you waste roughly 30% of your computational effort. Okay, so be it. But if you now go to 3 dimensions and you still have the same type of shock structure, you waste already half of the computation in vain. You compute, you solve optimization problems in parts of the state space where you really don't care, but you need it to get this global approximation right. But if you go to 10 dimensions, like the fraction is, depends on what geometry you're working on, is 1/t factorial. So like, it becomes very hard to have only a single point that is essentially relevant for your solution compared to the rest of the problem. So if you want to solve a 100-dimensional problem, the ratio is essentially 1/39. So like that means it's infeasible to use a grid-based method in a dumb way. So what does that tell you? We would like to have a tool that can do dynamic programming on irregular geometries in high-dimensional spaces, such that you actually approximate, your value and policy functions in the domain in the location of the state space where it matters. It can resolve nonlinearities, and so how can we do that? And one of the ways out is Gaussian processes, and so this is now what I'm going to talk for the next 20 minutes or so. So again, I know I'm a bit repetitive at this point in time, so my apologies, but just to fix ideas. So we want to be able to do value function iteration, so we want to be able to approximate high-dimensional functions, nonlinear functions on irregular geometries. What we now indeed want to do is we want to fit a function which is grid-free to data. So like, this brings me now to the theme of the top of the conference, which is machine learning. So like, assume I have a training data D, so it's a supervised setting, so I have X and Y. So for X, you could imagine is the state, Y would be my value function. I assume, my true function F, so my observed is Y is true function plus some noise. This is a standard assumption. Noise, you can imagine, can be, in our context, is the limitation of numerical accuracy. If you talk about data, it would be, limitations of measurement or whatever. But like essentially, this is the type of data I want. And now I want to find a way, to put a regression on top of it. And in particular, I want to put Gaussian processes on top of it. So before I come to the formal definition, so for those of you who never worked with Gaussian processes for function approximation, I deliberately put here an after lunch slide to make it explicit. So let's assume I have 3 observations at point x1, x2, x3. I have 3 function values. And I model the 3 function values jointly normally distributed with the mean 0 and some covariance matrix. And the goal that I have in the end of the day, given the data, given the model of my data, I would want to be able to make a prediction. So here at x star, I would like to know what is the most likely value of my function given the data I have. This is the kind of notion. Now, how would you choose the covariance matrix? So in plain English, it should somehow, if you're in the epsilon environment if you x1 plus epsilon, if you have a reasonable function, the function values should be relatively similar or like close to the previous function value. On the other hand side, if you're far away, so if you're at x3, the function had a lot of time or like space to change, so they should be little correlated. So essentially, the choice that you should make is you should choose a covariance function. If you're close by, covariance should be high. If you're far away, it should be 0. And this is again like intuition that I'm telling. Now you need to make, of course, a choice for this covariance function or this covariance kernel. And one of the functions that are most popular and intuitive to relate to is the squared exponential function. We will get to that in a moment. But essentially, it does that. If x and x prime are at the same, this values to 1. If they're far apart, they decay exponentially fast to 0. This is what you would like to have. Then you have also 2 hyperparameters here. We'll get to that too. So you have the characteristic length scale, and you have the signal strength, and you will need to somehow determine them based on the data to which you expose a Gaussian process. But so this is the baby example. Now, formally, what is a Gaussian process? So it's a distribution over functions. You need to assume a prior mean and the covariance function. I just talked about the covariance. The prior mean, in most of the applications, you can set it to 0. But what will happen is if you have prior knowledge about the function you want to model, you can, of course, cleverly choose the prior, because what will happen is outside the training set, you will decay back down to the prior mean. So like if you have a particular functional form in mind, you can help the training process a lot by choosing that. But anyway, for most applications, you set it to 0. And now, given that, you have the training data set, you have a model for your training data set. The question is now, how can you interpolate, right? And this is now actually quite cool. Bayesian, the Gaussians are so nice to work with. So essentially, here, what you do, I would like to know, given the data y, so that is my training set, I would like to know at the point x star, what would be the interpolator value. So what I do, I extend here my vector by 1, so that would be f x star. This is the quantity I want to know. I can trivially extend the right-hand side too, so I still model the entire thing as a joint normal distribution. And then what I'm interested in is the conditional distribution of f x star given the training data. And then if you do, again, like this is basic calculus, then you get an expression for the conditional distribution. And the mean, for this is an analytical formula. And for the variance, there's also an analytical formula. Now, why is this useful? Because here the mu, we will call it predictive mean. So it's the most likely value the function will have at this point. This is what I will use to interpolate the function. So this is very sexy. So it's, essentially just by some basic calculations, essentially you need only data, a way to invert matrices. Assume you know the hyperparameters. You need just a way to invert matrices. You can approximate functions in relatively high dimensions without a problem. And another cool feature of the Gaussian processes which will help us to make value function iteration very efficient is also the predictive variance. So that means you do not only know what would be the value to interpolate, but you also know what is the confidence level about the prediction at a certain point. So here I plot a simple example. The red points are the data. The blue curve is if you were to, the posterior, so like if you were to interpolate it. And then what I also plot there is the 95% quantiles. So you see essentially on locations in this, in the state space where you have no fat belly, but like it's very thin, you're very certain about your prediction. While in other locations of your state space where you have a big belly, you're uncertain. So that means, if you want to improve the quality of your function approximator, you would like to inject more observations there too. And now the beauty, and I'll get to that. So I'm in control of the data generating process. This is other two, the empirical guys that suffer from, you need to take what is there. My data generating process is a computer. So like if I need to improve the quality of my fit, I can do. But anyway, so that's the baseline. Now, it's another building block, of course. The kernel is an important choice that you want to make. The baby kernel usually everyone starts with. It always works, except it doesn't. Is the squared exponential kernel. It's essentially, you can think of that as a radial basis function. You can prove a lot of nice things. This is like the basic kernel you would choose if you want to fit Gaussian process to the data. But sometimes you have constraints on essentially the smoothness of your function. And this you can control with choosing other kernels. So Matern kernel, depending if you have like 3/2 or 5/2, you have a guaranteed C1 or C2. You can also choose periodic kernels. So if you have like time series with periodicity, you can pick a kernel that has a sine or cosine pattern. You can also compose kernels based on basic kernels, by addition. You can even use neural nets inside the Gaussian framework that would then be called deep kernels. So there's quite a fair amount of choices that you can make still within the Gaussian framework. And so there's this one guy that wrote an entire book on kernels. So just like if you ever get excited about kernels, that's a good reference. I'm almost there, so bear with me for a moment. Then, of course, like mechanically, so now we have a model for the data. Now the question is, I want to have the model that represents my training data as well as possible. And here, mechanics is the same as usual. So we would write down the log likelihood, and then you do, you apply, maximum likelihood, meaning you use some optimizer, can be gradient descent, stochastic gradient descent, like Adam. You can use some Newton methods. It's up on you. The important part is this is a non-convex optimization problem, so it really matters where you start, in the optimization procedure. Because like then, depending, what the data is and you start your optimization, you get different hyperparameters, and this can lead to quite different, posterior kernels then. And that means like you can get very, very wrong results. But anyway, so we have the model for the data. We have the ingredients like the kernels. We know how to fit it to the data. So we have a basic model. To fit a function. But most of the problems that you're facing, so far I didn't tell you how to sample the data well. An approach that you could take is, you say your model lives, say you have a basic idea of where consumption would live or where capital would live, or you name it, right? So you could uniformly sample from this domain. And as you know, like if you are in a high-dimensional setting, uniformly sampling, is a bad idea. It's very hard to fill the volume, right? It's just not very efficient. So the next question that we have now is, given a fixed computational budget, how do you place your your observations optimally in your computational domain. And let me make a concrete example. And then I go back to the theory. So like, if I were to uniform, or like, I just draw 5 points. I have here my analytical function. That would be the true function. I have here my red dots, and I fit the kernel, and the blue line would be what my prediction is, and the uncertainty related to that is like the blue belly here. Now, if I now just uniformly, or like I just randomly draw a point that is sort of idiotic, because like, here the uncertainty is the highest. So like I would like to have something which is algorithmically sound to add observations, where I need it the most. And for this there is an entire literature from reinforcement learning which is called active learning. Active learning essentially will tell you where to systematically add observations to your training set. So how does it work in practice? So I have my training set, a small sample, say 100 points or whatever, 100 points that are contained in my training set D. What I then do, I fit the Gaussian process over that. And then the next step that I do is I sample, say, 100 candidate points. And then I evaluate a so-called acquisition function. This is there's different acquisition functions, but this is a simple example. This acquisition function essentially contains the posterior mean of the Gaussian process that we have fitted. It contains the predictive variance of the Gaussian process that we have fitted, and then you have like two weights here, and so what you typically then would do is you would put a small weight on mu, because like this essentially just controls it controls for the level, and you would put a bigger weight on the second term because you want to minimize the variance. Then you, as I said, you throw in 100 points, you evaluate this expression. This comes at linear computational cost, so this is for free. Then you get a ranking for all the possible candidate points, how bad the prediction essentially is. And then the one or the few points that are on top of the list, you would add to the training set. Then you fit again a Gaussian process. Then you repeat that exercise. And with this mechanics, you essentially can populate the state space with observations where they are needed most. And I want to insist on this computational budget. So like, if, despite I'm telling you this is, very cheap afterwards, solving a lot of constrained optimization problems to fit the Gaussian process is not quite trivial. So you want to be efficient. So what you can do is say, okay, my computational budget is a maximum of, say, 1,000 observations in total. You start with, a few hundred uniformly sampled, and then you sequentially start to add points one by one, and then, your fit will be optimal. And again, 1,000 observations in a say, 10-dimensional space, it's very little if you think of it compared to, if you were to put 10 points per dimension, 10 dimensions, 10 to the 10, so 1,000 is like orders of magnitude smaller. So you really want to be efficient with that. Okay, so let me just, now I spent quite a fair amount of talking. So how does this work? So this is one. So like we would like obviously to add a point here. 1 point, fit is much better. Just single point, so much better. Add another point. Like with just adding 2 points, you can fit, something which looked terribly quite well. So active learning, is a very useful tool with very few observations to get stuff done. Okay, so that's second to last ingredients before we get to model. Now let me add one more. So we have way to efficiently approximate functions. But now the last elephant in the room is the curse of dimensionality. If you work, for instance, with with the radial basis, the radial kernels or so, you essentially always rely on the Euclidean distance. You have 1 over the distance of points. And if you go to high-dimensional states, high-dimensional problems, this Euclidean metric becomes uninformative. Essentially, you will have all observations far away on the surface of a ball. So like you lose the locality. But potentially we would like to solve 100-dimensional problems or 500-dimensional problems. So using Gaussian processes clearly doesn't work there anymore if you don't do anything about it. But luckily there is work, starting with a sequence of papers by Constantine. They introduced a method which called active subspaces. And just to fix ideas, this is similar mechanically to PCA, but opposite. So PCA, reduces the variance. So like, you have a projection on the variance of the input vector. This does the same thing on the output, so on the Y. So what do active subspaces do? So like I have a high-dimensional state space, X. So I want to find some projection matrix W that projects me in a lower dimensional space. I want to have that, in a computational way, or I don't want to have expert knowledge that I need to apply. In this lower dimensional reduced, lower space, I want to fit my Gaussian process because, if I have like a 100-dimensional problem, I can project it down to a 1-dimensional problem. Gaussian processes work magic, and then I go back up. So how can I do that in a principled way? So active subspaces, you could envision is essentially you want to find in your space the direction where you have most of the action, so to speak, and that's the dimensions you want to keep, and the others you want to ignore. So like in the example that I have here, what you want to find is you want to find a rotation. So on the left-hand side you have this 2-dimensional function. I want to find a rotation, like on the right-hand side, where this 0307 arrow essentially maintains most of the variation of the function, while the other one is flat, so we can toss that away. So that's the basic idea. Now, how do I do that numerically? I want to compute something which is a mean squared directional derivative is how Constantine calls it, but like it's a covariance essentially. So you compute this object here. So like you need to be able to somehow get gradients out of your function. So typically you sample, say, 1,000 points to construct this matrix. And now the same mechanics applies as if you were to do PCA. The next step is you do an eigenvalue decomposition and you sort the eigenvalues. You sort the eigenvalues and you look for gaps. And as a rule of thumb, so like Constantine wrote a book about it, but like as a rule of thumb, if you have like an order of magnitude jump in the spectrum, everything that is below, so like I write it here, you toss away. Now, so what does this tell you? So if you don't have a gap, dimension reduction will not be feasible. But it turns out, like for most economic problems, I solved literally 500-dimensional models. The active subspace was 1. So like it's quite surprising. You can get very far. Solving fitting a 1-dimensional function is trivial. A 500-dimensional function is kind of a beast. But you need to do this pre-computation first. But So here I just show an example. So for instance, here I write down some random 10-dimensional function. You do the eigenvalue decomposition. It turns out this object up there can be literally approximated by a one-dimensional function. So you sample that function on some points. You find this rotation. You have a one-dimensional fit, and I don't show you the convergence. Like, it fits perfectly well. Now, sorry for I feel like giving you an afternoon lecture after a nice lunch. So let me just wrap up here and then move to economics and finance. So again, the idea was I wanted to give you an overview of what tools from machine learning outside neural nets exist to solve dynamic stochastic models, and I think Gaussian processes are a very good tool. Now here the if comes, if data is expensive, that means if you need to solve optimization problems. Clearly, neural nets, they work brain dead. If you have a mechanics to generate a lot of data to fit the function, but if you have little data, Gaussian processes, I think are much more accurate, or not accurate, elegant. I just put here up essentially not so short table, to put things in perspective with other methods like sparse grids, neural nets, and Chebyshev polynomials. Those are sort of the tools that you may have used before to solve a dynamic model. So like the key advantage I really think is with Gaussian processes, you require way less hyperparameter tuning, and you have, compared to neural nets, and you have this option of uncertainty quantification, and this is particularly useful to do the Bayesian active learning. So that's kind of the takeaway why I like Gaussian processes a lot. And now I need to speed up a little bit, and I want to quickly touch on two dynamic models, and we'll show you why I believe Gaussian processes are useful. So the first one is a class of models dynamic incentive problems, right? So you all know them. It's like when two parties with repeated interaction under asymmetric information form a contract. So like it could be, you have a risk-averse agent that buys insurance from a risk-neutral planner against income shocks. So I will not go to the details too much, but let me just illustrate you a simple model in Word, and then why it's hard to solve, and why Gaussian processes are useful. So we have a prototypical insurance model. So we have infinite horizon, discrete time, again risk-averse agent that has privately observed income shocks. Then you have a risk-neutral planner who wants to provide an optimal incentive-compatible insurance against those shocks. And now the thing is, the agent reports his shock to the principal, but of course he could lie. And the entire goal of this exercise is you want to construct a transfer scheme that maximizes the principal's utility while delivering a predetermined lifetime utility to the agent. So again, afternoon. So that's how the setup actually works in more practical terms. So you have the principal that sits there, and then you have Dagobert down here. Here is he's rich. He has a high income. It's persistent. That's important here. If he got yesterday 1 million and the day before 1 million, it's very likely that he also gets tomorrow 1 million. But there is this few events where he can have a bad draw. Someone goes after his money, and then he's left poor. Then he's also, for a bunch of sequences, he's poor. And then he jumps back up to the state of the world where he's rich. But he never lies to the principal. So in this state of the world, he gets a transfer. In this state of the world, he needs to pay. So that's the basic arrangement or model that we're interested in. These types of models they're formally a disaster. They're fully, history dependent. There's not an obvious recursive formulation. So there was a lot of literature on actually how that showed that you can find a recursive formulation for dynamic incentive problems. And I'm not going to all the details, but one of the key insights was you need to introduce auxiliary state variables. They're called like promise keeping and threat keeping. Promise keeping and threat keeping utilities. So there are extra state variables. What they do is essentially they prevent the agent from lying. But I have shown you a baby setup with 2 types. Now you could, of course, imagine settings where you have way more types. You could also think of, of a tax schedule or something like that. So you may have 10 types. So the state space is n-dimensional with respect to shocks. That's one of the problems. And the other problem, so like potentially these problems are high dimensional, but like the really big issue is you don't know the feasible set. And this is disaster. So like you don't even know where to solve the model. And even if you knew, you need to make sure that on a strange geometry you can actually solve it. And this is exactly now, this brings us to Gaussian processes, why they're useful. So what can we do about solving this type of models now with Gaussian processes? So I'm not going about the recursive formulation. There's 2 or 3 tricks that we do. The first one is, essentially you need to be able to deal with infeasibility in your state space, and you don't know it ex ante. So like what people did in the past is, so there was a technique which is called set-valued dynamic programming. So what people did is, you first had to, with complicated geometric constructions, you had to find the feasible set, and then literally with Cartesian grids inside this set could solve the model. So like you clearly quickly die, that it doesn't scale up to anything beyond 2 dimensions. So what we do is, we said, okay, we want to completely get away from this issue of pre-computing the feasible set. So we reformulate the model with the penalty parameter, essentially. So forget about the details, but so what you can do now is you sample on the domain where inside there is somewhere the feasible set. Now, having this parameter, you could call it essentially, it's a choice variable. In fact, you could call it manna from heaven. So like whenever the problem would be feasible, this is non-zero. So essentially, we have some proof. So that means on an extended domain, we have all the nice properties of contraction, etc. So we can in principle solve it. But now we're anyway just interested on the location and state space where the model is feasible. And this now brings us to the next part. This brings us to Bayesian active learning. So we have this model. We draw samples on the domain. So here on the left, please look at the top left panel for now. So what we have a computational domain B. Inside there, somewhere is the feasible set where the model lives. That would be the V. So we draw a bunch of random points. Then we classify or we label the points as feasible and infeasible. Then, by simulating, we can populate, the simulation and Bayesian active learning, of course. We populate the state space here, where it's feasible. And so, like with relatively little effort, we are able to find the feasible set. And have a very high quality approximator of our value and policy functions where they matter. So this is from actual simulation that we did. Is you see essentially, I don't know if you can see it. So the blue dots is like where we start. Then you see the first 50, and then the second 50 points that were added with Bayesian active learning. And on the right hand side, that would be the resulting feasible set if you then evaluate the Xi classifier. So like, this is now a simple example, but this, we tested it out up to 10 types. And again, like people so far always just worked with 2 types. So going from 2 to 10 is a complete different beast. And this just worked essentially because we were leveraging Gaussian processes and what I showed you essentially over the last few slides before. So this is one application. Again, the message is you can solve dynamic programming problems on irregular geometries with funny features. Then the other problem that we looked at together with Fabio is the dynamic portfolio choice problems with transaction costs. And there the problem is similar. So you want to maximize expected lifetime utility given constraints. And you can essentially choose if you want to consume or you want to invest in a risk-free asset, a bond, or in risky assets. The fundamental problem there is similar. And I need to go a bit fast to allow for questions. So the problem there is similar. So the first one is the state space, as you will see in a moment, is irregular. So it's a simplex. So you cannot use grid-based methods trivially. That's why people usually got stuck with solving portfolio choice problems with. I need to be careful, like with non-trivial transaction costs. Like, of course, there's this entire literature that works with perturbation. They can deal with many, with a lot of assets. But like we look at non-trivial transaction costs where linearization doesn't work. So you need to be able to solve a dynamic programming problem on a simplex. That's the first issue. And then the second issue, you need to be able to detect inside already a complex geometry. You need to detect this node trade region. Which is also like hideously complicated in principle, and with Gaussian processes, this works relatively fine. So like here, that's the first point. If you can invest in risky assets, so it's clear. Either you put all in one and nothing in the other. So like, and if you go to 3 dimensions, you have this simplex. So this makes your life miserable from a numerical point of view. And then of course, Fabio also wanted us to have no, non-trivial stuff, like no short selling constraints and stuff. So this adds quickly complications also, like with respect to non-linearities. So that's kind of the problem. So I'm going here very fast. So like what you then do is you write down the Bellman equation. That's the first thing. Then you start to draw samples from this simplex. This you can do. Then you solve the Bellman equation. And so there's 2 technical issues. One is to approximate again like functions on this irregular geometry, but the other one is like you need to have a good way to determine the node trade region. So let me go to this point. So essentially, what we do mechanically is, and again, like I'm skipping here, dozens of pages of the paper. So we sample from the volume. Then we have a very elegant way to pin down the node trade region. So that would be the square which is colored in red. Then once you have the labels where you can classify, in which part of the state space you are, you can fit Gaussian processes. And what we now do in practice is we split the value function. We fit one value function over the node trade regions points, one over the other part. Then we do the recursion. Then you have an indicator function depending where you are to get the good function approximate. And then clearly again, with Bayesian active learning, you can add systematically observations to the problem. So again, so let me spend 2 more sentences and then I'm done. So what was this semi-lecture all about? So the key takeaway is that there is Gaussian processes in combination with Bayesian active learning and dimension reduction techniques like active subspaces, they provide an extremely powerful tool to tackle dynamic structural models in finance and economics under the condition that data is expensive to acquire. So I'm really insisting that there's a lot of those problems, and at the point where you need to solve a constraint optimization problem, you should really think twice before going to a neural net. Gaussian processes are extremely elegant. If I had to choose, so if I were, a mathematical object, and I would need to date a neural net or a Gaussian process, I would always go for the beauty Gaussian process, right? So that's the key message. They're very elegant. They can perform extremely well, but you need to know how to manage them. So that's one key insight. And then again, like from the 2 papers that I just quickly illustrated, is if you have problems at hand that have like non-trivial geometries complicated features, as you have seen with feasible sets that you do not know ex ante, or no-trade regions that you do not know ex ante. Gaussian processes then combined also with classification. So again, to come back to the theme of the conference, they can help you to address interesting structural problems. And with that, to stay on Swiss time, thanks for your attention, and are there questions?
Thank you for the splendid talk. I guess there's a gap in my understanding from the Gaussian process that I just introduced to us and the application in the dynamic programming questions. And so essentially my understanding, which might be wrong, is that we trying to approximate the optimal policy function by using Gaussian process. So, as a function of state variables, we generate, what the actual policy should be. And to be able to train that Gaussian process-based function, we seem to need a lot of training sample. And the training sample seem to come from solving numerically the dynamic programming problems. That is exactly where I sort of get lost. So because, for instance, you want to solve the value function under a certain values of the state variables, right? And then you are doing the Bellman equation and the iteration process. So arguably you need the value function at the value of other state variables as well. Yeah. So would you mind to explain a bit more how the Gaussian process interact with the process of solving dynamic problem?
Yeah, sure. So sorry, I probably went a bit fast here. So let me actually go to one of the slides that should be visible. So that's probably a good idea. So let's just think of for the moment in a line, okay? So let's say you have 10 points. At each of those points, I solve the Bellman equation, okay? So I have my functions. So I solve v equals max. I solve this on 10 locations of different states, okay?
So
then I have my training set. So I have 10x, you have 10y. I fit my function, but that's just to start, okay? I need to start with a guess of a function. Then when you do the recursion, on the right-hand side here, I plug in the v from the... So here I interpolate. So here I use the predictive mean from the previous iteration. So I do 10 points, solve the Bellman equation, fit the function. Then I go to the next time step. I solve the model again. But to solve the model, I need to interpolate on the previous iteration steps Gaussian process. So I carry around typically at least 2 Gaussian processes, one that has already been trained, and then interpolate on that, and the one that I'm currently building. And then if I have an infinite horizon model, you do that until you converged. And in the portfolio choice problem, it's a bit, it's a finite horizon model. There, it's a bit more subtle to find good, proof that you converged. But mechanically, is that what you asked?
Yeah, let me just confirm that I indeed understand. So you're saying that the training of the Gaussian processes happens at the same time that you iterate from the last period to the current period?
Yes.
Is that, okay.
Yes.
Yeah. Thanks.
What about computational tools that are available for us to work with Gaussian process? Because
there's a lot of good tools. There's like my favorite is GPyTorch, which is a library on top of Torch. Then there is this from Google on top of TensorFlow. I think it's in TensorFlow probability inside this Gaussian process. And there's a few others, but like I would really, if you're familiar with Torch, GPyTorch is really on top of it, and it has, pretty much everything that is just like it's state of the art to yesterday's publication in computer science. This is lovely.
Well, thank you very much for your inspiring talk. I just wonder whether you can quantify somehow, from a mathematical point of view, at least the order of the error of the approximation in some way, at least for some classes of problem. I mean, clearly will depend on n, will depend on d, and do we have an idea how this is going to change as n and d increase?
So, well, fair point. So I give you two answers, and you will not be happy about any of them. But let me. The first one is, there's for some classes of kernels, there's the universal approximator theorem, which is useless essentially. You just know that but it doesn't tell you how it converges. And then in terms of my models, so like for instance the dynamic incentive problems, I can show only contraction, but based on you're asking essentially, in the context of sparse grids, I know, for instance, in a Sobolev norm, I know what is the convergence rate, given some functions. I wouldn't be aware of any. So what you ask is like, if you add 10 times more points, if you have some smooth functions, how much would the error go down? I wouldn't be aware of that. Is that what you asked?
Yes, somehow. Well, you're telling me that it's going to converge, but I mean the question is how fast and what are the players there, D and N and so on. I don't know.
So look, I mean the problem. I mean literally this. In most of that work, like what you need to do is unfortunately, which is called VVUQ, so validation, verification, and uncertainty quantification. So like I can numerically show you, with a bunch of tests that it converged, but I cannot give you a sound proof. I mean, probably you could. I cannot. I can show you. Well.
So I really love your talk. I'm a kernel fan. So thinking about the implications that like the new way of doing business will have on the way we are doing business, would you say that running like Gaussian processes or deep Gaussian processes to different kernels will allow us, for instance, to identify like nonlinear factors in a very similar setup to the PCA, because you're talking about the active subspace?
So the active subspaces, yes, I think there was even there's a working paper by Brian Kelly and Semyon Malamud and some of his students. They used active subspaces. I'm not an expert in that, but like they recently started to do that, so it seems to work about the same. Sorry, and then there's also I didn't talk about this, but this generalization of active subspaces is by one of my co-authors, Bilionis. You can check it out. It's like they use neural nets, and then based on some information criteria, they find an architecture Well, I mean, you know, it's just think of a neural net with a bunch of hidden layers, right? And then eventually they will get down to say 1 or 2 or 4 output nodes. But you know, they apply it in physics for dimension reduction. But like they do that reduction of the neural net with, you know, based on the information criterion. So you could very well envision that this also works for reducing factors. But you know, this is clearly speculation. You should read the paper by Kelly and colleagues.
And moving away, so if we move away from the sparse, like for the limited data, there is also this, neural tangent kernels approach to Gaussian processes. And how is the inference in that area?
I didn't understand your question. You mean how that would play out in a dynamic programming problem?
Yes.
I don't know.
Okay.
I haven't tried. Sorry. You know, I mean, it's easy. You can plug it in. I don't know. Bad answer. I know. Sorry.
All right. Thanks.
Very interesting. Just a clarifying question on where the curse of dimensionality is. So in many of these dynamic programming, it is where you really have to solve the things on a grid. And so, for instance, in this case, what you have on, if the W would be like multidimensional. So where actually is the biggest curse of dimensionality here? Is it in the kind of decision variables or in the state variables that you really need to solve on a grid?
So here in the portfolio choice problems, you have risky assets, right? So you have many risky assets. So that would be the X. So you have 5 risky assets. You have like 5. You have a 5-dimensional state space at least, and then on top of that you need a global solution. You cannot do perturbation, so you need to approximate 5-dimensional function on this simplex, and within this simplex you need to figure out where this no trade region is. So this is a very small object. The volume is tiny. So to detect that is very hard. But the curse of dimensionality here comes from risky assets. In the context of the dynamic incentive problems, is the number of types. So you have 10 types. You have a 10-dimensional function, so the state is 10-dimensional that you need to carry around. And on the top of that, the state space will look like... just think of such a thing that you need to detect, but in 10 dimensions. This is very hard, again, the argument from the beginning. So if that's, say, simple to say that's a simplex, a 10-dimensional simplex in a 10-dimensional hypercube, the volume is 1 over t factorial. To detect that numerically is very hard. So that's kind of the problem is you need to approximate the function globally. I mean, on the geometry that you need to first find and then have a good approximation. So does that answer your question?
More or less. I need to think more.
Okay.